Algebraic Conditions for the Nature of Lines. Welcome, everyone. Today, we are moving on to a very important topic, the algebraic conditions for the nature of lines. Now, if you look back at our previous lessons, you'll remember that we learned how to find the relationship between two linear equations by plotting them on a coordinate plane. Drawing them out is a great way to see exactly what is happening visually. However, as you've probably noticed, the graphical method can be quite time-consuming, and if your drawing isn't perfectly precise, it can be difficult to tell if the lines truly meet or are just very close together. To solve this, we are going to learn a much more efficient way. We can actually use the coefficients, the numbers attached to our variables, to predict whether the lines will intersect, be parallel, or even lie directly on top of each other, which we call coinciding, all without ever having to pick up a pencil to draw a graph. This streamlined approach is what we call the algebraic condition method, and it's what we'll be mastering in this session. The general form of the equations. Now that we understand the goal, which is to move away from drawing graphs and instead use algebra to predict how lines behave, we need to talk about the setup. Before you can apply any of those algebraic conditions we are about to learn, there is one crucial rule. Both of your equations must be written in the standard general form. You can't just pick numbers at random from any equation. They must be organized. Let's look at how we represent these. We represent our first line as a sub 1 x plus b, sub 1 y plus c, sub 1 equals 0. And for our second line, we use the same structure, but with a sub 2 x plus b, sub 2 y plus c, sub 2 equals 0. To be clear about what we are looking at, the sub 1, b, sub 1, and c, sub 1 are simply the coefficients and the constant term belonging to that first line. Similarly, the sub 2, b, sub 2, and c, sub 2 are the coefficients and the constant for the second line. Keeping these organized is vital, because in the next few slides, we are going to be comparing the ratios of these specific numbers to determine if our lines intersect, stay parallel, or overlap completely. The three algebraic conditions. Now that we have established that our equations must be in the standard general form, with all our coefficients and constants clearly identified, we can move on to the core of today's lesson. By comparing the ratios of the coefficients of x, the coefficients of y, and the constant terms, we can categorize the pair of lines into one of the following three cases. Essentially, we are looking for patterns in these ratios to predict exactly how these two lines will behave on a graph, whether they will cross, run parallel, or lie directly on top of one another. Case I: intersecting lines, unique solution. Now that we have established our standard general form in the previous slides, let's dive into our first specific case. Case 1: intersecting lines. Imagine two lines that are not running in the same direction. If you calculate the ratio of the coefficients of x and find that it is not equal to the ratio of the coefficients of y, these lines will eventually cross each other at exactly one single point. Mathematically, we express this condition as a sub 1 divided by a sub 2 does not equal b sub 1 divided by b sub 2. When this condition is met, we describe the nature of this system as consistent because a solution does exist. And specifically, because the lines cross at only one point, we say there is exactly one unique solution. This is the simplest scenario to encounter, as it represents a clear, single point of intersection on your graph. Case II: parallel lines, no solution. To identify this algebraically, we look for a specific pattern in our ratios. We are looking for a situation where the ratio of the coefficients of x is exactly equal to the ratio of the coefficients of y. But, and this is the crucial part, neither of those is equal to the ratio of the constant terms. In mathematical terms, the condition is a sub 1 over a sub 2 equals b sub 1 over b sub 2, but this is not equal to c sub 1 over c sub 2. Because these lines never intersect, they share no common points. Therefore, we describe the nature of this system as inconsistent, and we say that there is no solution to the system of equations. This is a sharp contrast to the first case we discussed, where a unique solution existed. Now that we have seen how intersecting lines work in case 1, let's move on to case 2, which describes a different relationship between the two lines. Imagine two lines that run perfectly side by side, like train tracks, so that they never, ever meet, no matter how far you extend them. These are what we call parallel lines. Case III, coincident lines, infinitely many solutions. Now, let's move on to our third and final case, which is case 3, coincident lines. Up until now, we've looked at lines that cross at one point or lines that run parallel and never meet. But what happens if the two equations are actually describing the exact same line? This occurs if all three of our ratios, the ratio of the x coefficients, the ratio of the y coefficients, and the ratio of the constant terms, are all equal to one another. Mathematically, we express this condition as a sub 1 over a sub 2 equals b sub 1 over b sub 2, which equals c sub 1 over c sub 2. Mathematically, we express this condition as a sub 1 over a sub 2 equals b sub 1 over b sub 2, which equals c sub 1 over c sub 2. When this happens, the lines lie directly on top of each other, meaning they are coincident. In terms of the nature of the system, we call this consistent and dependent. Because the lines are overlapping everywhere, they don't just meet at one single point. Instead, they share every single point along the line, which means we have infinitely many solutions. In the next slide, I'll show you how this looks in a real-world scenario involving taxi fares. Real-world application example. Now that we have mastered the 3 algebraic conditions for comparing ratios, let's see how this works in a real-world scenario. Imagine you are trying to decide between two different taxi companies. Company A and Company B, both companies calculate their total fare using a specific formula based on a fixed base fee and a rate per kilometer. To represent this mathematically, we can use linear equations. For Company A, the cost equation is 2x plus 5y minus 100 equals 0. For Company B, the cost equation is 4x plus 10y minus 200 equals 0. In both of these equations, x represents the distance traveled, and y represents the time spent in traffic. As we move to the next slide, we are going to use the ratios we just learned to determine if these two companies are actually charging you differently, or if their pricing structures are essentially the same. Step-by-step analysis. Now that we have our two taxi company equations from the previous slide, let's walk through the actual calculation to see how they relate to one another. We'll do this in 2 clear steps. First, let's perform step 1, which is to identify our coefficients. Remember, as we discussed in slide 2, we need to look at the numbers in front of our variables and our constant terms. For Company A, our A1 is 2, our B1 is 5, and our C1 is negative 100. Now, looking at Company B, our A2 is 4, our B2 is 10, and our C2 is negative 200. Next, we move to step 2, where we calculate the ratios. This is the most critical part of the algebraic condition method. We need to compare the ratio of the x coefficients, which is a 1 over a 2. That gives us 2 over 4, which simplifies to 1/2. Then, we check the ratio of the y coefficients, which is b1 over b2. That is 5 over 10, which also simplifies to 1/2. Finally, we check the ratio of our constant terms, which is c1 over c2. That is negative 100 over negative 200, which, as you can see, also simplifies to 1/2. As we prepare to move to the next slide, take a moment to notice that all 3 of these ratios have come out to be exactly the same. Conclusion from analysis. Now let's look at what our calculations actually tell us. As we just saw in the previous step, the ratio of the x coefficients, the ratio of the y coefficients, and the ratio of the constant terms are all exactly the same. They all simplify to 1/2. Because all 3 of these ratios are equal, we can conclude that these two lines are coincident. This means that if you were to graph them, they wouldn't just be parallel. They would lie exactly on top of one another, forming a single line. In the context of our taxi company example, this leads us to a very important conclusion. The the pricing structures of Company A and Company B are actually identical. Even though the numbers in the equations look different at first glance, the underlying cost logic is the same. Therefore, any combination of distance traveled and time spent in traffic that results in a specific fare for Company A will result in that exact same fare for Company B. Moving forward, we will look at some common pitfalls to watch out for so you don't make mistakes when identifying these ratios yourself. Common mistakes to avoid. First, watch out for the incorrect standard form. As we discussed in slide 2, everything must be in the form a sub 1 x plus b sub 1 y plus c sub 1 equals 0. A very common mistake is to leave a constant on the right side of the equals sign. For instance, if you see an equation written as a sub 1 x plus b sub 1 y equals negative c sub 1, you must move that constant to the left side first. If you don't, your value for c sub 1 will have the wrong sign, and your entire ratio comparison will be incorrect. Second, be extremely vigilant with sign errors. This is where many students lose marks. When calculating your ratios, pay close attention to whether a number is positive or negative. For example, if your constant c sub 1 is negative 5 and your constant c sub 2 is positive 5, the ratio of c sub 1 over c sub 2 is negative 1, not positive 1. A single missed minus sign can make parallel lines look like coincident lines. Finally, ensure you are comparing the correct ratios. It is easy to get confused when looking at a long string of numbers. Remember, you are comparing the ratio of the x coefficients, which is a sub 1 over a sub 2, to the ratio of the y coefficients, which is b sub 1 over b sub 2. Do not accidentally compare the x coefficient to the y coefficient within the same equation, such as a sub 1 over b sub 1. You must always compare the same type of coefficient from the first equation to the same type from the second equation. Now, before we wrap up our lesson with the final summary table, I want to pause and discuss some common pitfalls. Even if you understand the logic of the ratios, small errors can lead to the wrong conclusion. Keep these tips in mind, and you will find that applying these algebraic conditions becomes much more reliable. Key takeaways. All right, we have reached the end of our lesson. To wrap everything up, let's look at this summary table, which brings together everything we have discussed today, from the initial ratios to the final algebraic interpretation. Think of this as your ultimate cheat sheet for exams. Let's start with the first row. If you find that the ratio of the x coefficients is not equal to the ratio of the y coefficients, that is, a 1 over a 2 does not equal b1 over b2, graphically, you are looking at intersecting lines. Because they cross at a single point, we call this a unique solution, and in mathematical terms, we say the system is consistent. Moving to the second row, this is a very important case to watch out for. If the ratio of the x coefficients is equal to the ratio of the y coefficients, but neither of them is equal to the ratio of the constant terms, written as a 1 over a 2 equals b1 over b2, but not equal to c1 over c2, the lines are parallel. Since parallel lines never meet, there is no solution, and we classify this system as inconsistent. Finally, the third row represents the case we saw in our taxi company example. When all three ratios are perfectly equal, meaning a 1 over a 2 equals b1 over b2, and that also equals c1 over c2, the lines are coincident, meaning they lie exactly on top of each other. This results in infinitely many solutions, and we describe this as a consistent and dependent system. If you can memorize this relationship between the ratios, the graphs, and the consistency, you will be able to master any problem involving the nature of linear equations. Great job today!